hello everyone. I'm Jiashua from Tsinghua, and it's my great pleasure to hear our recent research here. And the title of my talk is an inductive modeling of distribution shifts enhances trustworthy AI. And my talk is based on joint works with Jose, Peng, Jiajing, Mihaela, and Nabil. And the works are done when I was a visiting student researcher at Stanford and Cambridge. And today I'll introduce my research from these four aspects. And the first one is the overview. And here I'll briefly share the background of distribution shift. As we all know, machine learning algorithms have been widely applied in prediction and decision-making systems in real-world applications like policy making, bank loans, and medical diagnosis. However, there are many real-world challenges of AI systems. For example, biases exist in AI systems, and if we look at the first figure, the AI system can correctly predict the label of this object. However, it cannot in the second for the second figure. But the only difference is the skin color, and it shows that there's a huge bias in AI systems, and it's a huge challenge if we would like to use trustworthy and fair AI system. And the second challenge is the generalization problem, and where we often see many examples where AI systems make mistakes. And here's one example. In this figure, the car kept jamming on the brakes, and it was thinking that there's a real person in front of it. And clearly, it's an out of distribution sample here, and so it's make a huge mistake. And also, here's another example where AI camera ruins the soccer game for fans after mistaking referee's bald head for the real football, and it kept tracking on the referee rather than the football, and so it may do some harm for the game. And also, these examples show that there are many real-world challenges for AI systems in practice. And therefore, in this talk, and our key point is that building a reliable AI system requires a holistic view, including data collection, model training, model evaluation, and also model deployment. Like most of the previous research mainly focused on model training stage, where we have many kinds of model architectures, many kinds of training algorithms, and many kinds of loss functions. However, what we are calling for in this talk is that we need to shift the focus from model training to model evaluation and also model deployment, which may be even more effective to deal with distribution shifts and also to enable trustworthy AI. And here to make it clear, as for the previous philosophy, it is from assumption to algorithm. For example, for causal algorithms, people may just assume that there's a causal structure and there are no hidden confounders. And then based on these kinds of assumptions, people begin to design many kinds of causal algorithms. And also for distributionally robust optimization methods, which is like a typical method from operations research. And people assume that the test distribution is near the training. And so if we can protect the worst case distribution around the training, our model can stay robust in practice. However, the key question is that do those assumptions really hold in practice? The answer is probably not. From this maybe famous paper named In Search of Lost Domain Generalization. And here the authors show that actually domain generalization methods, they cannot outperform empirical risk minimization. And which means that even if we have developed so many robust methods or domain generalization methods, there's little progress compared with empirical risk minimization. And so it's a huge problem. And here we think that maybe the key reason is that their assumptions may not hold in practice, so it makes their algorithms not work in practice. And so in this talk, what we are calling for is maybe we need to shift the focus from model training to model evaluation and also model deployment. And it is super important for us to really understand what kind of situations we are in, and also to understand our model's performance in greater details. And also we need to understand the distribution shifts. And in this talk, I will share maybe 3 tools for this kind of understanding, and which span maybe 2 stages. The first is for the model evaluation. And here first, we would like to introduce a tool to understand your model's stability under potential shifts that may occur in the future, and which we call the model stability evaluation. And also, we will share a tool to understand your model's underperformed regions within one distribution, and which we call it risk region analysis. And also, even for the deployment stage, we would like to share one tool to understand your model's performance drop between 2 distributions, and which we call the performance drop diagnosis. And for these 3 tools, and actually the high level idea is that we really need to understand the model performance and the distribution shifts better, which can enable even more efficient model improvements. And this is a big picture of my talk. And then we move on to the first tool, the model stability evaluation. And here the key problem is how do we evaluate the stability of a learning model under some kind of data perturbations? And here a learning model may be neural networks, and also it may be large language models. And when we are talking about data perturbations, actually there are mainly 2 kinds of perturbation. And the first is data corruptions, which means that sometimes our samples can be perturbed or can be changed. And from a language of probability, it's like the changes in the distribution support. And the second kind is subpopulation shifts, which refers to the perturbation on the probability density or mass function, and while keeping the same support. So these 2 are orthogonal dimensions. And here we give some examples. As for the data corruption, and here a typical example may be the LLM jailbreak. For example, if we ask a harmful question to LLM and it will refuse to answer. However, if we slightly change the input question, for example, we can do some role playing, and also we can add more background knowledge, and then maybe it can answer this kind of harmful question, and it's not desired. So this is one example of data corruption, which means that sometimes the input data can be perturbed, and then our model performance will be maybe super bad. And then here's an example for subpopulation shifts, which means that there may be a majority group and also a minority group in your training data. And after we train our model, and our model may pay too much attention to the majority group. However, it will ignore the minority group. For example, Amazon's AI recruiting tool has been found to show bias against women. And this shows that AI systems can be biased against the minority group. And we refer to this as the subpopulation shifts. And before we move on to our methodology, and we would like to introduce maybe a different distance function here, which we call the optimal transport discrepancy. And here the high level idea is that compared with the original optimal transport, which is computed in the sample space, and here we lift the original sample space to a higher dimensional space, which represents a joint sample and density space. And in this way, we can, if we calculate the optimal transport distance on this joint space, we can capture the data corruption and also subpopulation shifts at the same time. And here we choose the cost function as this. The first term captures the difference between two samples, and the second term captures the difference in the probability mass. And in this way, we can capture both kinds of data corruptions at the same time, both kinds of data perturbations at the same time. And here we go to the formulation of our stability measure, and which is actually to solve an optimization problem. And here the objective is to minimize some kind of distance between a distribution Q and the original distribution P hat. And here the constraint is that in distribution Q, the model performance will drop to a predefined threshold R. And this is what this objective means. And actually, this criteria captures the minimum level of perturbations required for model's performance to drop to a predefined risk threshold. So you can imagine that the larger of this score means that your model is more stable because you need to do more perturbations to destroy your model. And otherwise, your model is less stable. And when we solve this optimization problem, and we have like two things. The first and we can get two things. The first is this kind of score, and the second is the most sensitive distribution of your model. So based on this stability evaluation, and so we can know like so what is the most sensitive direction of our model. So it may produce even more detailed understanding of the model performance. And here we provide an intuitive illustration of our measure. And actually it computes the projection distance to the distribution set where the model performance falls below a specific threshold. And here this sphere means captures the distribution set where the model performance is not good.
Excuse me, Joshua.
Yeah.
For me, I don't know. For the others, at the moment the screen is a bit fuzzy. I don't know if others have the same problem. Can you?
Is it fuzzy?
It's
the same problem.
So maybe it's a problem of connection, a speed of connection on your side. But so this one, yeah, we see things in it's not very good picture. We see everything as a bit fuzzy. So this one we can read it. Yeah, now it's good. Can you move to the next one? Yeah, now it's good. Okay, so let's hope that it will stay the same. Sorry about that.
Okay, cool. Yeah. So it works now, right? Okay.
Now it is okay. This is not. Now this is very good.
Okay, cool. Yeah. And yeah. And here actually our metric, and here this sphere means captures the distribution set where the model performance is not good and it falls below the predefined threshold R. And this point is the original distribution. And actually our metric computes this kind of projection distance. And also if we solve this optimization problem and we can get the distribution Q star, and then Q star captures the most sensitive direction where we can destroy our model in an easiest way. So that's what our stability measure means. And based on our formulation, we prove that the strong duality holds. And also with the strong duality, we can derive the dual reformulation of our objective. So we can, based on this dual reformulation, we can compute our metric easily. And also we can compute our metric for neural networks and large language models. And here we provide a visualization on toy examples. And actually here is a binary classification task. And so before I previously I mentioned that our metric considers two kinds of perturbations at the same time. And here to demonstrate this, for the last two figures, for example, for the third figure, we only consider data corruptions. And also for the last figure, we only consider subpopulation shifts. So you can see that for these two figures, we may have to do much more perturbations to destroy our model. So if we do too much perturbation to sample or to the density, so the resultant distribution may not be realistic. However, if we consider both kinds of data perturbations at the same time, as the second figure, you can see that we don't have to do too much perturbation for each dimension, but it is more realistic. So this is one example to demonstrate what our perturbation or what our most sensitive distribution is like. So it's like the second figure. And then we would like to introduce 3 use cases for our model stability measure. And the first one is we would like to analyze the stability of different MLP models. And here the task is to predict individuals' income based on some personal features. And here we compare 3 models, which are both MLP models, but they are optimized via different. And the first one is the original empirical risk minimization. And the second one is adversarial training, which is designed for robustness to data corruptions. And the third one is tilted ERM, which is designed for robustness to subpopulation shifts. And here in this figure, we change the relative ratio of 2 kinds of perturbations. If we look at the left side, our metric consider data corruptions more. However, on the right side, our metric considers subpopulation shifts more. And here, if the curve is higher, it means that your model is more stable. And here from these results, we can see that actually a method designed for one class of data perturbation may not be.
There's a suggestion that you deactivate your camera so that the network concentrates on the picture. Can you do that?
Because yes, hi, Joshua.
I don't know.
Yeah.
I don't.
Does it work now?
Sorry about that. It's not.
It's not really working, I think. Not for now.
Okay, cool. Yeah.
It's still a bit blurry, but I think we have to live with it. Sorry about that.
Oh, I see.
Maybe you can put it on in full screen. I think the problem might come from there, from the fact that.
You mean I? What should I do?
Like to switch on full screen mode, like on presentation mode.
Yeah. It is already the full screen mode. Yeah.
So we have to do So sometimes
does it work now?
Sometimes it appears clearly. At the moment, it's a bit blurry. So I think you really have to explain in detail so that we understand what is on the screen.
Okay.
But,
cool.
But you can turn on your. I think you can turn on your video because actually it didn't make a difference.
Oh really?
Yeah. For some reason, so you can just put it on back on.
Okay, sorry for that. I don't know why the network is unstable. Maybe it's because I'm in China and that's a huge distance between us. Yeah. So should I?
So let's go on.
Okay. Yeah. And here from the results, we can see that actually a method designed for one class of data perturbation may not be robust against another. So here, if you look at the blue curve for the adversarial training, you can see that on the left side, it is stable. However, on the right side, when we consider subpopulation shifts, it's similar to the traditional empirical risk minimization. And also, it's the same for tilted ERM. It's not stable under data corruptions, but it's stable under subpopulation shifts. So it means that when designing like robust methods, we really need to think more carefully what kind of data perturbations we would like to deal with, or what kind of data perturbations may occur in practice. And the second use case is for large language models. And here the task is question answering tasks, which consider like two kinds of questions. The first is general question, and the second is harmful questions. And here we compare 6 general LLMs. So since this work was done last year, so here the LLMs may not be the SOTA LLMs recently. And to adapt the cost function for LLM, and here we need to redefine the perturbation distance between two sentences. And actually, imagine for the minimal data perturbations, we would like to preserve the semantic meaning of our input question. And also at the same time, we would like to ensure the sentence length is similar to the original. So we don't add too much information, and also we do not lose too much information during the perturbation. So our new cost function is like this, where we use a combination of semantic similarity and also the token number ratio to capture the perturbation distance between two sentences. So this is our new cost function, and based on this, we can solve the optimization problem, and then we can compute the stability score of different LMs. So this is the results. I'm not sure whether this figure works. And here from the results, actually, the insight is that LM evaluation is very complex, and we should not only rely on one single metric. Here from the figure, if we change the relative strength of two kinds of perturbations, and also if we change the predefined error rate, you can see that the rankings of LM change based on different patterns of shifts and also the error rate. So it means that when comparing two LMs, we should not only rely on one specific metric, which may produce unreliable comparison. And also we surprisingly find that there's a trade-off in stability between answering harmless questions and not answering harmful questions. For example, if we look at the dark red curve in both figures, we can see that Mistral 7B model performs super well on harmless question answering, but it is super bad on not answering harmful questions. So I guess a possible reason is that the good semantic reasoning ability makes it easier to be cheated by some role-playing prompts for people to do the jailbreaking. So these are the insights for the LM stability analysis. And also we find that actually our stability measure allows us to compute the feature stability. So here the high-level idea is that we can only perturb. We would really like to know perturbing on which feature will cause model's performance drop. And also, if we do feature stability measure, we can provide more fine-grained diagnosis of our prediction model. And here to achieve this, actually it is super easy. For example, if we care about the ice feature, and we can only allow perturbations on this kind of feature, and we can at the same time we can keep the other features the same. So we can change our cost function like this, where we assign infinite weights on any perturbations on any other features. So based on this cost function, we can compare the feature stability among different features. And here's the result. The task is to predict individuals' income based on personal features. And from this result, we surprisingly find that actually both the neural network and also logistic regression model, they focus too much on one specific racial feature, which is the American Indian. So it is not good because it will introduce potential fairness problem. And also based on this result, we find that feature stability can motivate a better and also a more efficient algorithm intervention. For example, for adversarial training, we do not have to perturb all the features. So we can only perturb this identified sensitive racial feature, American Indian. And after doing this, we find that it significantly increased the worst racial group accuracy compared with previous MLP models and also MLP model and also logistic regression model. And also it outperforms the original adversarial training method. And this finding aligns with the empirical findings in our previous paper, which maybe you can refer to for more details. And so this is for our first tool, the model stability measure. And here are the takeaways. This tool is a stability measure for machine learning models for both neural networks and large language models based on optimal transport. And it considers different data perturbations at the same time. And also it helps to understand why your model fails. And it can guide targeted algorithm interventions. So the whole pipeline is like you can first try to diagnose your models, and then you understand its failure modes. And then based on this understanding, you can improve your model more effectively. And if you are interested in this tool, you can refer to our papers for more details. And then we move on to our second tool, the risk region analysis. And compared to the first tool, it is super simple and it's super easy to use. So here the problem is beyond the overall performance. How do we really understand where our model performs well and where not? And here we propose a super simple but effective method. We can just fit a decision tree to predict the sample loss from the covariates. And in these two figures, actually the contents and also the text do not matter too much. And I just want to show two examples of our safe region and also the risk region from a simple decision tree. And here you can see that the safe region and the risk region are formalized by some decision rules. So it is highly explainable and it can be trusted in practice. So here are just two examples from our previous work. And also we find that this kind of risk region analysis enables smart deployment in practice. For example, for a single model, the error rate on the validation set is about 15%. And the error rate on the test set is about 20%. However, for the safe region we identified, the error rate is below 5%, which means that you can almostly trust your model on data from the safe region. So it is easy to judge whether the data is from safe region because we have decision rules for our safe region. And also for the risk region, we can see that the error rate is even above 50%, which is even worse than the random guess. And it means that please do not use our model on data from the risk region. So if we can have better understanding of our data, and also if we can have fine-grained analysis of our model's performance, it can enable some kind of smart deployment in practice. So we can choose where to trust our model and where to not trust our model. So this is our second tool, the risk region analysis. It's super simple. Yeah.
Yes. Can you say again how you define the safe region and the risk region? It's by learning decision trees. That's what you do.
Yeah. So it is super simple, and we for tabular data we just fit a decision tree to predict the loss of a data point from the feature of the data point. So we just build a new prediction task and we use a decision tree.
So and it's something that, as you said, it's something very easy. And it should be done everywhere. Why don't people do it always do it? Because it's very important to be in safe region or risky region.
Yeah. And so actually in our takeaways, and we think that actually we may need more ways to capture the safe region and also the risk region. And also if you are interested in this, you may refer to our 2 papers. And also there's a branch of methods called error/slice discovery, and where I guess the goals are similar, and so there may be even more methods to achieve this. And certainly it requires even more methods to do a better job here. And here we just provide a super simple way to achieve this. Yeah. And here's our second tool. And then we move on to our third tool, the performance drop diagnosis. And here, we would like to deal with one situation. It is when observing the performance drop, how to attribute the drop to each feature. And if you look at this figure, the situation is like we train our model on one distribution P, and then we deploy it in another distribution Q. And actually, we do not know what happens in the test distribution Q, and we only observe the performance drop of our model. And here, we would like to call for an inductive way to deal with this kind of performance drop, where we need to first understand the performance drop. And then this kind of understanding can inform better future improvements. And also to clarify, this work is designed for time series data, but it can also be used for static data. And actually, first, we just try to do some kind of transition. We would like to transform a time series prediction task to some kind of static attribution problem. And here we just extract multiple temporal properties from time series data. So when we are doing the attribution, we can only deal with static data. And here we define as for the attribution, and we first define the conditional risk as this. And here x delta minus s means that all the other features in x delta except the feature s. And here are the 2 conditional risks, and the attribution score is defined as the gap between 2 conditional risks. And here you can see that actually when we are interested in one specific feature S, and if we would like to compute its attribution score, we would like to control the distribution of all the other features the same between P and Q, and then we compute the performance drop. So now the performance drop should be only attributed to this specific feature S. So this is our high-level idea. And to be honest, it's similar to average treatment effect estimation in causal literatures. And here, if you take the S as an empty set, and then this attribution score captures the eigenvax shifts between 2 distributions. So this is our attribution score. And also to compute this, we can borrow the doubly robust estimator from causal literature, and then we can compute this score in a more reliable way. And also we characterize some theoretical results for our estimator and also for our problem, where we can exactly prove the unconfoundedness and also unbiasness. And also we capture the consistency of our estimator. So if you are interested in the theoretical part, you can refer to our paper, which will be listed as a final part of my slides. And here we show maybe two results. The first is 2 case studies. The first is for the age shifts in mortality risk prediction tasks. And here we use MIMIC3 datasets. And the original model to be evaluated is transformer. And here from the results, first for the first figure, we can see that our attribution method correctly attributes a preference drop to some age-related features, like age and admit location and some previous ICU stay time. And also more importantly, in the last two figures, we show that actually based on this diagnosis, we can achieve simple but effective model intervention. For example, if we find age is the most important feature, and then we can do some simple balancing in the training data, and then we can retrain the model. For example, we can balance the different age groups by do some sample reweighting, and then we can retrain the model. And from the results, we can see that actually compare with if you just fine tune your model on the new data from the test distribution, the accuracy is here as shown by the orange bar. However, if you do the model intervention based on our diagnosis, we do not use more data. So the data used by these methods are the same, but we achieve much better performance on the test set. So this means that actually the diagnosis can enable more efficient model improvements. And also for the primitive diagnosis under temporal shifts. And here we show that now our attribution method can identify some temporal properties as the most important features. And here, as for the first feature, we random sample like 10 samples from two distributions. And as you can see here, there are huge difference between these two kinds of distribution on this simple feature. So this shows that actually our attribution method makes sense and is useful in practice. And finally, here are the takeaways of our third tool. And actually, we need an inductive way to deal with different shifts compared with simply fine-tune the model on the test set. And also understanding different shifts is super important, and more methods for this are needed. And also you can refer to our paper for more details. And here is the for our third tool. And finally, I'd like to make an advertisement. And recently, we have made a Python package for distribution knowledge robust optimization, which is a typical branch of methods in robust optimization and also in operations research community. And it contains 14 DRO formulations and 9 backbone models, from linear models to tree models to neural networks. And here's the link for our document, and the package has been released at GitHub, and our paper will be soon released. And so that's and here's are the references. And so that's all of my talk, and thank you so much for spending time with me, and please feel free to ask if you have any questions. Yeah.
Thank you so much. Thank you. I see people uploading. Usually I'm not, so first a question, some logistics. Usually I'm not asking for the presentation material for the file, but this time, if you can send me the PDF, because it has been blurry on the screen for many times, so we could see from time to time the detail, but not very often. So this time I would like to get the PDF in order to make it available for everyone if they want to get all the references and look at all the detail. So please send it to me.
Sure.
Thank you. Thank you.
Sure.
I ask for, please raise your hand if you have some question. So your tool, you have tools for the 3 topics that you mentioned, I guess, because this Python tool contains everything. Is it, yes, so there's a question about accessing the recording and the slide. So usually, sorry, I'm doing the logistics first. So usually the recording is published on the YouTube Conscience AI YouTube channel, and it's also available from the ATRASS website. There is a link to the recording. But this time we will also publish the slides, and I don't know exactly how we are going to do that, but we will do it maybe on the website directly. That would be probably the best way to do that. I will ask our colleagues from Responsible AI UK to put the PDF file on the website. Now,
Sure.
okay, for the tool, is it something that can be easily integrated with popular other tools? I'm thinking, for example, of scikit-learn. Would all the features be made available in scikit? I don't know if you know scikit-learn. It's a rather popular machine learning tool with millions of users. So would that be? I think there's a lot of Python in scikit-learn. So do you think there's it can be used in the different settings? Let's say.
I do think they can be used because there are some basic methods and they do not require too complicated implementation. And also we plan to release another package which contains this all of these tools, and so I guess they can be easily used in different scenarios and also applications.
Have you tested how all these tools scale up with the size of the data of the model, etc.?
Yes. So for now, these tools are designed for tabular data, and but also if I guess it's easy to extract some properties for image data and also language data. And now we are working on scale up these tools for language models and also for language data. But for tabular data, I think it can perform well with even larger data set size. So it may not be a problem. Yeah.
Okay. Well, because in Confidence d'Intérêt, we worked also on time series, a big time series, which in the form of tabular data, but really big tables. So that would be interesting to look at. Can you stop sharing your slide, because then this is anyway, it is blurred, and so that we can see you instead.
Yeah. Okay.
So Martin, please.
Yeah.
Yes, thank you for this presentation, Joshua. I have a very, say, high-level question about this inductive way of addressing machine learning. Well, from what we could see, it was clear that at the same, there's this very curious thing that at the same time that you have rather simple intervention proposals, you have rather complicated mathematical formulas. At least I know for the audience here. But I also do know that the inductive approach is precisely what makes that little difference. Like, as in the formulas. If the formulas are complicated, it's not because your work is overly theoretical and so on, but rather that because you're trying to first infer hypotheses, no matter how difficult they are, but still not just stay in the realm of experimental kind of statements, but actually manage to come back to the formal, right? Is it like this how we should understand?
Yeah. I think you are right. Things actually for most of the works previously dealing with distribution shifts, and I guess the most important problem is that we just make too many assumptions without checking them seriously. So if our assumptions do not hold in practice, and so you can imagine that the resultant algorithm may not work well. So here, the inductive way means that we need to first really understand what situations we are in and what kind of distribution shifts we are faced with. And so based on this kind of understanding, we can also design many complex methods to deal with our specific situation, but it will be more effective because we have understood our situation, and also we have understood what kind of problems we are faced with. So that's the key idea for this kind of inductive way to deal with shifts.
Okay, Martin.
Okay, thank you.
I'm coming back to this question that we discussed shortly during your talk about what you call the risky region and the safe region, if I remember well. In Confiance.ai, we worked a lot on what we call the ODD, operational design domain. So we say that a machine learning system should only be used in its operational design domain. And I think I'm wondering if it corresponds to what you are calling the safe and risky domain in your case. If it's the case, then we, as I said, we should always use your this. I mean, build decision trees or whatever to do that, because it's really very important when you are working on critical systems.
Yeah. I agree. So actually here for the decision tree is a super simple and I guess the basic way to do this. And also I guess we may need more advanced way to better capture the risk region and also safe region and or the ODD. Yeah. So I think.
So you consider that for you the safe region is what we call the ODD.
Yeah. It's a region where the model performs well and you can trust your model. So it's like the average loss is super low in this region.
I think that it's a topic that Thomas will also address because he has been very, very much concerned with the question of ODD in his program.
Maybe before that, if I can just add one thing, I think that there was one distinction that we made in Confiance AI between the model ODD and the system ODD. And what I think is super interesting about Jashu's work is that it has been difficult to tie down ODD in terms of like dimensions like luminosity, blur, and so on, top down. But in here, it's like you infer them from the loss function. So you are having this top-down approach that kind of meet halfway with a top-down approach usually done for ODD. So yeah, I just wanted to make this little comment.
Yeah. So how stable, maybe just one comment on this. I'm very much interested in this position.
Okay, yeah, go on.
Can you hear me? Like, I'm just wondering how stable is this process of learning this region using decision trees, like from your experience?
Actually, I think it's super stable because it's only a simple decision tree. And however, there are many other advanced methods, maybe from error-slice discovery, and they use more complicated ways, but I think they are less stable. But for decision tree, it's easy, and also it's easy to control the size of the region and also the number of the regions you'd like to choose. So it's simple, but it's maybe more stable. Yeah.
Interesting.
Okay, there's a question waiting by Suyan Sai. Suyan Sai.
Hi, can you hear me?
Yes.
Just to clarify, when you say ODD, I think in this process you actually talk about OOD, right? The out of distribution and the in distribution, because you're using the model's loss function. It's not the OBD, but it's more the.
Have you heard? For me, the sound is really bad. So can you ask the question? Either you speak slowly because the sound is really bad, or you put the question on the chat so that we understand your question.
I think I understood it. Yeah, okay. It was essentially if you can relate these regions with the notion, like, are they not simply the same of saying in here you are in distribution or you are out of distribution, right?
Here for the region analysis, we focus on one distribution, but data are different, like the training data, validation data, and also test data. But the distribution is the same. And as for the region analysis part. Yeah.
Okay.
Okay, thank you.
So what is the status of your tool, your tool in Python? Is it open source, free for everyone? Are there some licenses around? Or?
Yeah, actually for the region tools, it is open source at GitHub. So but it's in another package. So I guess we are working on like combining these tools together into one package, so it's maybe easier to use. Yeah, and we will do this soon, I think. But for the region analysis, the code is already open source at GitHub. Yeah.
I'm asking this because there is a Confiance.ai catalog available online, and I don't think that your tool is part of the catalog because it hasn't been tested in our program. The tools that we published have been tested on different use cases, and obviously not on your tool hasn't been tested on the use cases that we were using in Confiance.ai. I don't know if we have the means to do that in the future, but really that I would. It's the typical tool that we would like to include in the catalog when appropriately tested in some critical use cases such as the ones that we have. So, or maybe have you thought? We also there's an open challenge at the moment which is on Renault data about welding, so images of weldings to decide whether they are good or to be redone. The challenge, I think, is open until I can't remember the date, but it's still open. Maybe that would be an opportunity for you to test the tools on the welding data. These are tens of thousands, something like, I can't remember the number, but maybe 10 or 20,000 images of welding. And we have the answer of they are either good or not good. The link, Martin put the link for the challenge.
Okay, I can take a look.
That would be if you have some time to devote to that, you could even win. Who knows? So okay, I take advantage of this to do the advertisement for the welding challenge for everyone. But okay.
Yeah. Okay. Yeah.
Any other question? We still have 2 or 3 minutes before we give the floor to Thomas. I'm looking in the chat whether there are some questions or there are only links and chat. Links in the chat. No more question. Okay. So thank you very much.
Thank you so much.
It was not easy because of the bad quality of the pictures. Not your fault. The fault of the network. But I think we have heard the essential, and we will publish the files so that everyone can look at the equations in detail and the pictures, etc. So
Thank you so much.
Thank you again.